The next thing we're going to talk about, and we might have actually mentioned something about this the other day, I can't remember, Heron's formula. Finding the area of the triangle by using another formula. Now, the other day, first off, let's talk about all the different ways you can find the area of a triangle. If you're given the height of a triangle, you're given the base of a triangle, then you can use the area formula. Area is equal to 1/2 times base times height. In this case, 1/2 times 8 times 6. 1/2 times 8 is 4. 4 times 6 is 24. Next scenario. If you're given angles inside a triangle. Now, if this is your case, where you're given, this is a 40-degree angle, this side is 7, this side is 9, you had your new formula to use, to where it was 1/2 AB times cosine, or times sine, excuse me, sine C. 1/2 times the side times the sine of the included angle. There's another method. Third method. Anytime you have a triangle and you're given all three side lengths, 6, 7, 8. You're given all three side lengths, you can use Heron's formula. Now, Heron's formula is derived, and that's the reason it's thrown into this chapter, because you're going to say, well, where's the sine, cosines, and tangents? It's derived from from those formulas. So the area is equal to, and they use the letter S. S is what's called your semi-perimeter. It's your perimeter divided by 2. It's half your perimeter. So area is equal to the square root of S times S minus A times S minus B times S minus C, where A, B, and C are your three side lengths. Okay, let's work the problem they've got made up for us here. A piece of property in downtown Houston is advertised for sale at $45 a square foot. If the lengths and size of the triangular lot are 220, 234, 160 feet, what's the asking price? So $45 a square foot, of course, we're going to use that last. We're going to find the area. We're going to find how many square feet are in this lot. And then once we find that area, we're going to multiply by 45 to see the price. So you got this triangular lot, side lengths of 220, 234, and 160 feet. The area is equal to the square root of, first thing we need is a perimeter. Somebody's got a calculator there. Find the perimeter for me. 220, 234, and 160 gives you a perimeter of 614, which gives you a semi-perimeter. We'll call it S. Semi-perimeter would be 307. Okay, you don't want your perimeter, you want your semi-perimeter. So the area is equal to the square root of the semi-perimeter times the semi-perimeter minus A, the semi-perimeter minus B, the semi-perimeter minus C. That makes sense. 307 minus 220, I believe is 87. 307 minus 234, 673. And 307 minus 160 is 147. Type it in your day. The square root of 307 times 87 times 73 times 147 as a decimal. Let's give the approximate here. But leave it on your calculator. Is there a decimal after that? 16,930 point.
That's actually 29.
Okay, 29.6 what?
68.
All right. Everybody good with that? Square feet. And again, leave it on your calculator because we're going to pay $45 for each of those square feet. So we're going to do that answer times $45 a square foot, and we get a rather large asking price. What do you get for an asking price on that? Nearly $1 million. How big is that lot? I guess it's downtown Houston. I don't know. I don't know the going price for property in downtown Houston. But a 220 by 234 by 160 feet lot, that's pretty expensive. Next up says a central angle. We're getting back into some geometry now. A central angle alpha and a circle of radius r intercepts a chord of length a. Write a formula for a in terms of alpha and r. Okay, going back and this, you don't have to know all this, but just a review of geometry. A central angle always has the center of the circle as its vertex. That's what makes it a central angle. When you're dealing with central angles, let's say that looks like it's about a 30-degree angle. If this angle is 30 degrees, for your ACT reasons, this arc would also be 30 degrees. Okay, they're not asking us for the arc. They're saying the length of this chord. A chord is a line whose endpoints, a line segment whose endpoints are on that circle. So we've got a chord, and we want to write a formula for A in terms of alpha and R. Well, I noticed something that it looks like we could use either our law of sines or law of cosines in order to find us a formula, but I don't think we're going to be able to use law of sines because we have alpha and A, but we don't have either one of those other angles. So let's use law of cosines. A squared equals B squared plus C squared minus 2BC times cosine A. To write a formula for A in terms of alpha and R. Plug it in, plug in all the values you know. It's going to work out kind of nice because if we let this be angle A, angle B, and angle C, then A will be A. So you got A squared equals, what's B and C equal to? And we're doing a formula here. We don't have any numerical values. We're doing a formula, and hopefully after we finish, you'll see kind of what we're going for here. What are both B and C both equal to? The radius. R squared plus R squared minus 2 times R will be R squared again times the cosine of A, which is alpha. And again, you see now the relationship here. If you were given the radius, if you were given a circle, and we're fixing to work a problem like this, if you're given a circle and you know the radius, well, it's going to be the same thing as this radius. Let's say the radius was 3. And you know what this angle was, then you know the exact length of that chord by using this formula we're fixing to put together. That is the formula, but let's clean it up some. R squared plus R squared we can put together, so we now have A squared equals 2R squared minus 2R squared times the cosine of A, or cosine of alpha. And how tempting it is to delete those, right, to mark them out. 2R squared minus 2R squared, that's 0. The only problem is this 2R squared has something attached to it. This is not plain old just 2R squared. So what we can do, though, what I would do, is I do A squared equals, since there's 1 in both terms, go ahead and factor it out. 2R squared times 1 minus cosine alpha. The reason I factored it out, so I wouldn't have to write it down twice. Right. To get A by itself, we can get rid of the squared by doing A is equal to, you don't have to put plus and minus because it's always going to be positive. So let's just deal with the principal root. A is equal to the square root of 2R squared times 1 minus cosine alpha. One more step, R squared. Since there's 3 things in those parentheses, 3 being multiplied together. If for any of those 3 things, you can take the square root of it, you can pull that out front. Or if this was like a square root of 8R squared, if there's a perfect root included in any of these, you can pull that root out. So what I'm going to do is I'm going to take this R squared, pull it out front. So A is equal to the square root of R squared will be R when you move it outside of that square root symbol, times 2, 1 minus cosine alpha. Normally, well, remember back, we didn't really have to worry with it, but the square root of R squared, sometimes you have to put some absolute value bars around that. But when you square something and take the square root of it, it's always going to be positive anyway. And the radius is always going to be positive anyway. You really don't have to worry about that. What about 1 minus cosine alpha? You're still thinking about last chapter, and you're still thinking about, is there any simpler way I could write that? Had that been cosine squared, you can still use those identities that we talked about last chapter. 1 minus cosine squared, you could change to sine squared because of the Pythagorean identity. So as you're working through these problems, if you notice the answers are different from what you're getting, there's a possibility they might have took something like this and used an identity to simplify it. But what I want to do, we're fixing to work a problem on this next page that involves this formula we just made up. So let me copy it. And on the next page, paste it. So we can use it. Because what that does is A was the arc length, A was the chord, R was the radius, and alpha was the central angle there. And what they're giving us on this problem, they're saying take a circle that has, let's see, find the length of the chord intercepted by a central angle. Let me draw that central angle. A central angle of 33.8 degrees in a circle that has a radius of 22.4 feet. All radii are equal. So what we want to know is how long would that chord be? If you've got a radius of 22.4, what's the distance from there to there? Well, could we use law of cosines again? Yeah. Do we have to? No, we got a formula. We just made it up. The length of a chord is equal to the radius times the square root of 2 times 1 minus the cosine of 33.8. You see the beauty of some of this stuff. If you've got in your job that you're working, you're having to do something like this over and over and over and over, and you're having to use the law of cosines over and over and over and over. Well, sometimes you can take that formula that you've been using, turn it into a new formula, simplify it a little bit, and it's a whole lot easier to type into your calculator. Instead of having to do that long, drawn-out law of cosines over and over and over, now we have a little simple formula. Let's see what we get. We got 22.4 times the square root of 2 parentheses 1 minus cosine of 33.8. 13.02. So that formula that we just made up, usually the length of a chord intercepted by some central angle given a radius. Any questions? A robotic arm. And back when I did robotics at my previous job, this is the type problem that was presented to me. Let's say that you've designed this robotic arm, and you've got 2 pivot points here. You've got a pivot point here, a pivot point here. And you want to see, and this was actually a problem similar to what we faced one year. Let's say that your robotics arm is here, and you've got something you need to pick up, I don't know, here. You need to know, can you pick it up? And not only can I pick it up, but what angles of rotation do I need? Where am I going to pivot this and this to where I can pick it up? What kind of angles do I need? And that's what this problem's asking. It's saying a robotic arm with a 0.5 meter segment. Here's the 0.5 meters. And that's set. You know, I say it's set. You can design a robotic arm to extend, right? You can put some gears in there to actually make them reach out and in. But for this robotic, that's set. It's not going to grow any longer. A robotic arm with a 0.5 meter segment and a 0.3 meter segment is attached at the origin. The computer-controlled arm is positioned by rotating each segment through through theta 1 and theta 2. We want to know, given that we want to have the end of the arm at the point 0.7, 0.2. You want to pick something up there. Find theta 1 and theta 2 to the nearest tenth of a degree. Let's go ahead and not just find the angles they're asking us for. Let's go ahead and pretty much solve this thing. Let's find all of our different angles. The way we're going to do that, let's see, we're given, how much information do we have? We do have this distance, whether we know it or not. This is the point, 0.7, 0.2. How can we find this side length? How can we find side length B? Any ideas? Say again. distance formula, or which is the same thing as the Pythagorean theorem. This distance here is 0.7. This distance here, 0.2. That's your hypotenuse, so that would be your c squared. So 0.7 squared plus 0.2 squared is equal to c squared. So you're going to do the square root of that on your calculator. So our b value there is then about 0.73. Okay, and that is a rounded answer. So we want to make sure if we want an exact answer, we might have to do something to get an exact answer to that. So let's see. Now we've got 3 side lengths, and what can we do with those 3 side? Which honestly I don't know if we're going to need all 3 of those side lengths, but we found them all. That's pretty much how far from the origin your object is located, and we know that we can reach that. Should be able to reach that because our reach on our arms are 0.5 and 0.3. It can reach up to 0.8, so that's within our reach. Let's see, what we want to find next. Let's go ahead, let's find this thing. I believe that's omega, lowercase omega there. The reason I want to find that angle is this goes back and reviews us a little bit. Law of sines, law of cosines is great, but 2 chapters ago we learned something that when you're dealing with right triangles, you don't have to use this law of sines and law of cosines stuff. You can use basic SOHCAHTOA. SOHCAHTOA only works when you're dealing with right triangles. If you notice here, you look for this, and this is going to be a real good review for what we're about to start, which is actually vectors. Mostly with vectors, you deal with SOHCAHTOA. So in case you forgot it, here's how you do it. If you're looking for this, and again, I believe, don't quote me on it, but I'm pretty sure that's a lowercase omega. If you're looking for lowercase omega, you got a right triangle here. You're given the opposite side of that right triangle, and you're given the adjacent side of that right triangle. That'd be a tangent problem. The tangent of omega, that's a bad omega. The tangent of omega is equal to opposite over adjacent, 0.2 over 0.7, which, again, let me show you a trick here. Just basic. You don't have to do this. I'm just showing you. 0.2 over 0.7, anytime you've got decimals in a fraction, if you wanted to, you can multiply top and bottom by 10 there, and you can just dump those decimals completely. That's 2 sevenths. 0.2 over 0.7 multiply top and bottom by 10, that's the inverse tangent of 2 sevenths if you don't even want to put the decimals in there. So that angle is equal to, move the tangent over by doing inverse tangent, and somebody give me that angle. So omega is equal to about 15.9 degrees. And again, if you were dealing with this problem in real life, I would be storing every one of these values. We'll leave it rounded for now. I think our answers will be close enough. So 15.9 degrees. Let me erase some of this stuff. Go ahead and put that down. That's 15.9 degrees. Now let's use our law of sines, cosines, and all that, and find some of this other stuff. Given that the side lengths are 0.5 and 0.3, I guess we could find, and 0.73, we could find beta. We'll do it first. Your formula is, if you want to look back, instead of a squared equals b squared plus c squared, is b squared equals a squared plus c squared minus 2ac times the cosine of b. That's one of your other law of cosine problems, or formulas. Plug in everything that we know. I know that b is that 0.73. And if you had that stored in your calculator, that's when you would want to pull up and use the exact value. I know that a is 0.3. And I know that c is 0.5. Any questions there? Watch how I type this in. I think we could do it in 2 steps. Solving that equation, if you don't remember from the other day, move this and this over first. So you got 0.73, or if y'all got the exact version, type it in there. 0.73 squared minus 0.3 squared, that's not squared, minus 0.5 squared. And I'll go ahead and do enter there. So I moved over this and this. Now I've got to move this over. Since it's being multiplied times cosine of b, I would do the answer divided by, in parentheses, -2 times 0.3 times 0.5. So the cosine is equal to -0.643. Quiz you for a second. That negative sign being there, what does that tell you? Somebody know? The cosine is equal to -0.643. We're dealing with a robotic arm. We're dealing with a triangle here. Angles of rotation between 0 and 180. Well, I mean, we could have a 179-degree angle in a triangle. A negative cosine angle. Where's it at? No, fourth quadrant would be positive. Sine would be negative 4. Cosine are x values, right? X is positive here. X is negative here. It's bigger than 9. It's in obtuse angle, is what it tells you. Anytime cosine is equal to a negative, it's going to be an obtuse angle. Back to my calculator. So the cosine is equal to 0.643. So I'm going to do the second cosine of that answer. It gives me about 133 angle. We call it 130.0. So beta, is that what we're looking for? Beta is about 130.0. Did anybody use the exact and get anything? I didn't have score. Do what? 130.3. Okay, so it wasn't much off, but it was off a little bit. Let's use that exact though. Use the exact version. She said you get 129.3 degrees. And you see, you know, that you would think that would make a big difference. Eventually it might. Boy, this is a long problem. So beta is equal to 129.3 degrees. And again, if you got the exact version or exact answer on your calculator, I would store it because we're fixing to use it again. Because now we need to find alpha. Which, by the way, we could find theta 2 now. You'll see theta 2 there. We want to know how far down you're going to have to rotate that arm. Okay, imagine it being straight up in the air. We're going to rotate it down, then we're going to pivot this end down. If this angle here was 129.3, y'all see that straight line? It's called a linear pair. Those two angles are going to add up to 180, so this theta 2, which we can now find, theta 2 would equal 180 minus that 129.3, which I believe is 51.7 degrees. That's one of your two angles of rotation. You're going to pivot that second part of the arm down 51.7 degrees. Is it 50? Thank you very much. 50.7. Now let's find this other pivot angle. We know that this is 15.9 degrees. In order to find this, let's see, is there other methods to do this? I was fixing to say if you knew what this was, because you know that, well, no. If you had these two values, you could just use basic sine, cosine, tangent, but I don't think you have the hypotenuse length, but you don't have either one of these values. If you had either one of those values, you could just use basic sine, cosine, tangent. But you don't, so what we're going to have to do is find alpha. I'll use another color for alpha. I'm telling you, you can get pretty deep into this problem. There's a lot of information that you can find using those. So here we go. I think now we can use law of sines, though. The sine of 129.3 over the side across from it, which is 0.73. You'll see an issue there already. Both of those are rounded answers. So that's the reason I said you might want to store them. Both of those are actually rounded answers. Equals the sine of, we're looking for alpha. The sine of alpha over the side across from it, which is 0.3. I'm going to type it in as is. Mary, if you still got it stored, type in the exact. We'll compare the difference. So you got 0.3 times the sine of 129.3 divided by 0.73 And then that isolated sine of alpha, so now let's move sine over by doing the inverse sine. And you get about 18.54 degrees. Is that what you got? Pretty close? Awesome. So we'll call it 18.5, that's rounded the same. I guess it's two negatives since they were both, it's kind of weird, since they were both rounded, one might have rounded up, the other one might have rounded down, it kind of hit in the middle again, it kind of worked out. So that means that alpha is 18.5 degrees. We're done now. Because if this is 15.9 degrees, this is 18.5 degrees. 15 to 9, 18.5, that would be 34.4. That whole angle would be 34.4 degrees, which leaves you rotating down, since that whole thing is 90 degrees, that'd be a rotate down, theta 1 would be, let's see, the rest of the 90 degrees, 55.6. So, we did all that to program a robot. Now let's talk about robotics. There's two different types of robotics. You've got, I can't remember which it was, autonomous, I think is what it's called. And then you've got your remote control type. You got one that pretty much you sit down and write a program of I want the robot to do. And I think some of y'all did that, didn't you? Didn't y'all do robotics in Saints? To where you wrote the programs. You said, okay, first I want my robot to do this, then I want my robot to do this, and you wrote the program for it. You see how this would apply to that? If you had a robotic arm that you needed to drive up to something and then the robotic arm to reach over and pick it up, you would have to use something like this. You would have to find out, okay, how far do I pivot this? How far do I pivot this? Then how far will I pivot this in order to reach down, pick it up? Then you got the more fun type, which is the remote control. To where it doesn't matter. You don't have to program anything like this. Remote control, you got your RC, you got your actual control there, and you can just drive over it. Then on, okay. But you can see, like with writing a program, you would need these values if you're doing something autonomous.